Today we're going to talk about the concept of work. And before we talk about that, it's important to remember, or for me to review, another concept that you need to understand or recall that we've talked about probably in other classes that you've been a part of, and that is the concept of conservation of energy. Always remember that energy cannot be created or destroyed. It only changes form. Because a lot of times this is going to be the key to finding the answer to many of the problems that we're going to undertake to perform. And so I wanted to bring that to your memory before we move through the rest of this chapter. Now, work is the product of the component of force in the direction of motion times the distance through which that force acts. So it's the component of force times cosine theta times d. It might be more reasonable or better to put this cosine theta next to the f, but because of the parentheses and stuff, I ended up doing it this way. But remember that theta is the angle between the force vector and the displacement vector. So here's some examples of situations where work is being performed and work is not being performed. The first example is a person that is doing work. And here, the force vector is actually down the handle here. And F cosine theta represents that part of the force that's acting in the direction of displacement. So you would have F cosine theta times this distance. And that would be the work that's being done on this lawnmower by this individual exerting this force. Now this next guy is not moving. He's exerting a force. He's holding this bag, but it's not moving, briefcase. Therefore, D is equal to 0, and therefore no work is being done. Now this next one might be a little bit more difficult to understand, but notice that the force is up and down, but the displacement vector is from left to right. So the angle between these two, at least regarding this force, the angle is 90 degrees, and the cosine of that angle is 0. Therefore, despite the fact that the briefcase is moving, it's not moving up and down, which is the direction of this force, and therefore, in this situation, no work is being done. There's no transfer of energy in this situation. Now, I know that sometimes people have a hard time understanding that, but that's how this is done. This next one, the briefcase is being carried up the stairs, so that the displacement vector is up the stairs. The force vector is straight up. Therefore, the angle is theta. So the force parallel to the displacement vector is F cosine theta. And that represents the work being done carrying it up the stairs. Lastly, you have a situation where the force is exactly opposite the displacement vector. So when this briefcase, starting up here and is lowered, the energy is transferred out of the briefcase and into the generator. Here the work is done on the briefcase by the generator, but because it's in the opposite direction of the displacement, the work that's being done is negative. So it's actually removing energy from the briefcase and transferring it to the generator. That's because they're in opposite directions. And when it goes down, we'll talk in the future about gravitational potential energy. The energy that it's actually removing is the gravitational potential energy. So let's do a calculation with this fella. This was the first one we looked at the previous slide. And let's put some numbers on here. So how much work is being done on this lawnmower if he exerts a constant force of 75 newtons at an angle of 35 degrees for a distance of 25 meters? And here's the calculation. You have F cosine theta times D. So 75, which is F, cosine theta, which is cosine 35 degrees, times 25, the distance, if you do the math here, you get 1,536 joules. And joules is the most common, that's a Newton meter. So it's the most common unit of energy or work that you'll be working with. Now, if you graphically look at this, the top shows what happens when you have a constant force. Constant force of F cosine theta. So you have a straight line that is parallel to the x-axis because it's a constant force. The x-axis represents the distance over which this constant force is being exerted. And the area, the shaded area, represents the work that's being done by this force over this distance. So if you graph force parallel to the displacement, so F cosine theta, if you graph that and on the x-axis put displacement, you end up with a line, and the area of this line is the work that's performed. Now, in a situation where the force varies, then you have a line that goes like this. And because you have a line, in order to estimate the work, you'd have to divide this up into equal little boxes and take the area of each of these little boxes. This is the interval displacement. That's why it's called di. And if you add all these up, the area up, then that's the work over that interval. It's an estimation of the work. You notice that these boxes don't fit exactly right. So it's an estimation of the work that's done. Now here's a situation where we're going to talk about something called work or net work. And the net work is essentially the result of a net force. Remember, when we worked previously, we sometimes had an applied force and a force that acted against that applied force, so we would end up calculating the net force. When you have a net force that exerts over a particular distance, here it's shown at 0.8 meters, here's the friction force of 5 newtons and the applied force of 120 newtons, you can see pretty quickly that you can subtract this from this and get a net force, and then if that is applied over this distance, you can do that calculation. However, you can also use the mass and the acceleration to do the same kind of calculation. And let me show you. And also, there's a way of calculating the net work by looking at the mass and any change in velocity that occurs. Because this applied force minus the net force or friction force should result in a change in velocity or an acceleration. And you can use that to calculate the work done. So again, net work is the work that's done as a result of a net force. Again, it's the component of that work that's parallel to the displacement vector. So you always have to take that into account. Now, if you take that equation that we just wrote, and let's just assume for a second that we don't have to think about the cosine theta, you can express the net force as a mass of the box times the acceleration of the box. So you can change this equation and make it look like this. And then using equations that we had in the previous chapters, this acceleration can be expressed as the difference in velocity squared divided by 2 times the distance. And you remember that v squared is equal to v0 squared plus 2ad, okay? And if you rearrange that, then you end up with v squared minus v0 squared. v0 squared is the initial velocity, and the final velocity is v squared. And this is the distance, and then you have another distance component here. And if you put this distance cancels this one, okay? And you end up with mv squared minus mv squared, and each of those is divided by 2, so it's 1/2 mv squared minus 1/2 mv0 squared. You can look at this in the book if you're having a hard time following my talking about it, but essentially what you end up with is the final kinetic energy, which is what this represents, minus the initial kinetic energy is the net work that's performed. So it's another way of calculating the work from the velocity, the change in velocity, if that's what you have, if that's what you know. And this is called the work energy theorem. This relates the work done to the kinetic energy change that you see. Now, I said kinetic energy. This is actually known as the translational kinetic energy because there's also rotational kinetic energy. And this is the energy that's produced by any particular velocity of an object that it has. This work energy formula or theorem is important to keep on your card for the next test, and to use potentially on the next quiz. So let's take a look at a problem and see what we can do with this. We have boxing gloves, and boxing gloves are padded in order to lessen the force of a blow. So calculate the force that's exerted by a boxing glove on the face if the compression of the padding is 7.5 centimeters in a blow from a 7 kilogram arm brought to rest from 10 meters per second. Okay, so this is the distance that this happens, and here is the mass, and here's the change in velocity. Okay, so you should be able to use the numbers we just looked at to do this problem. And here's how you do it. So the net work, and here's the work theorem that work energy theorem that we just put in there. Now the final velocity is 0. It goes from 10 to 0. So V is equal to 0. V0 is 10. So the work net is equal to 1/2 times 7, which is the mass of the arm, times 10 squared, or 350 joules. Now, if the work net is equal to the force net times the distance, and we'll assume that there's no theta to worry about, that it's 0, then you take the distance. The force would be equal to the distance, or the work divided by the distance. And so the force ends up being 4,670, or 4.67 times 10 to the third newtons. Now let's see what happens in the bad old days where they use bare fists. So the distance falls from 7.5 centimeters when there's padding to 2 centimeters, which is just whatever padding's on a person's knuckles by chance. And you can see now that all the velocity stuff doesn't change this first calculation, so you still have 350 joules of work done, but now it's done over 2 centimeters or 0.02 meters, and the same work is done over that, so the force goes up to the 17,500 or 1.75 times 10 to the fourth newtons. So you can see that putting a little bit of padding, about 5 centimeters of padding, which is about an inch, a little over an inch, actually it's almost 2 inches, results in a significant drop in the force that's delivered by a blow. Now, I mentioned a few minutes ago gravitational potential energy. Gravitational potential energy is the energy that something has because of its position in space, based on a baseline that you have to define. If the work that's done to lift a weight is stored in that mass and Earth system by something known as gravitational potential energy. So the work performed by lifting this mass, this distance, using this force times this distance, is stored in what's known as gravitational potential energy. And so that's the work that's done here. And this formula right here represents the gravitational potential energy. Work equals mass times gravity times the difference in height. As the weight moves back downward, the gravitational potential energy is then transferred. As it moves down, it's transferred from the weight to the clock. So it passes, the chain passes through here, and it basically transfers the energy to the clock, and that's what keeps the clock moving. So gravitational potential energy is equal to the mass times gravity times the difference in height of when the weight started and when it finished. And that's a formula you need to keep in hand. So we'll stop at this point and go on to part 2. So you have 2 equations at this point. The work mass, or the work energy theorem, which is 1/2 mv squared minus 1/2 mv0 squared is equal to the work net done. And then the gravitational potential energy, which is m times mass times gravity times the difference in height when you move an object.